So in the last video, we introduced RD and started talking about convergence RD, copying wherever we could notions from one-dimensional analysis. We're going to keep on doing the same thing here. So we're going to say that a subset E of RD is a bounded set if the norm of the elements of set, that is, this is a subset of R, is bounded in the usual one-dimensional sense. So we're just copying that notion of boundedness and applying it to higher dimensional objects. When we do that, a lot of the theorems are going to translate over immediately. So in particular, the Bolzano-Weierstrass theorem, you can state again in RD and it remains true without changing any of the words. So just to recall what that means, the original Bolzano-Weierstrass theorem said, every bounded sequence has a convergent subsequence, and using our new notions of boundedness and convergence, that actually remains true exactly as stated in RD. I'm not going to give a full proof with all of the notation because the notation is a little bit heavy, but I'll give a little bit of a sketch. So let's assume that xn is a bounded sequence. Then in particular, xn of I is also bounded for all I in 1, 2, all the way up to d. So these are all bounded sequences. And therefore, using the original Bolzano-Weierstrass, we know that xn of 1 has convergent subsequence, which I'll call xn 1 of 1. Okay? So this is a subsequence of the original sequence, and it converges. But we can keep on going. xn 1 of I is also bounded. Right, because it's a subsequence of a bounded sequence, so the original sequence is bounded, the subsequence is certainly also bounded. And therefore, by Bolzano-Weierstrass, xn 1 of 2 has a convergent subsequence, which I'll call xn 2 of 2. And we can keep on playing this game, right? Now xn2 is a subsequence of the original xn1, which is a subsequence of xn, and so that's bounded as well, and so xn2 of I is bounded for every I, and therefore xn2 of 3 has convergent subsequence, which I'll call xn3 of 3. And we keep on doing this, and at the end, we find that we get a convergent subsequence xn d of d. Okay, so we have this sort of sequence of convergent subsequences, but it stops, right? When I have these ellipses here, there are only d steps in total that I'm doing. There's no infiniteness here. For any particular d, I could actually write out all of these steps, although, of course, if you told me that d was equal to 200, it would take me a long time. What's the upshot of having done all of this? Well, xn1, that was a subsequence of the original sequence, and furthermore, it was convergent along the first coordinate. xn2 is a subsequence of xn1 that was convergent along the second coordinate. But it was a subsequence of xn1, so it's actually convergent along the first coordinate as well, because remember, any subsequence of a convergent sequence is itself convergent. xn3 is a subsequence of xn2, which is convergent on the third coordinate, but therefore it's also convergent on the second and first coordinates. And so at the end we get to xnd, which is convergent along the dth coordinate, and because it's a subsequence of all of the previous subsequences, it's convergent along all of the other coordinates as well. So that means that actually xnd of I is convergent for all I, and that means that also xn itself is convergent, because we know that a sequence in RD is convergent if and only if all of the coordinate sequences are also convergent. So that's a short sort of a proof sketch of Bolzano-Weierstrass. The only part that's a little bit sketchy here is that there are so many of these subsequences lying around. And if you wanted to really keep track of them, you'd probably want a little bit of extra notation, but hopefully this is convincing, and if you feel like it, you could pull out all of the details or open up the textbook, which has them lying around. Okay, so that's Bolzano-Weierstrass. It really is true, and that really is a proof. I've merely sort of condensed it a little bit so it's easier to see on the screen. All right, so that's actually most of the class in R converted to the language of Rn. And just for a little bit of practice, we're going to prove one of the old theorems, something that we did way back close to the start of the course, in this new context. So here's a theorem that we proved a long time ago, which is about the uniqueness of limits. So that is, if xn converges to some limit a, and also the sequence xn converges to some number b, then in fact a is equal to b. So we proved that in one dimension before when a and b were numbers, and we're going to prove the same thing in Rd when a and b are vectors. And actually, if you go back, the proof is going to be almost identical. So what is that proof? We're going to fix epsilon greater than 0, and we're going to check, well, since xn converges to a and xn converges to b, there exists some n depending on epsilon, so that for all little n bigger than big N, xn is within epsilon over 2 of a, and xn is within epsilon over 2 of b. So this is sort of the usual boilerplate, so I go over it quickly. And then we actually have to do the calculation, and we're just going to be using the sort of usual add 0 trick followed by the triangle inequality. So a minus b is equal to a minus xn plus xn minus b. And then using the triangle inequality, that norm is less than the norm of a minus xn plus the norm of xn minus b, which itself is less than or equal to epsilon. Since that's true for every epsilon greater than 0, in fact, the norm of a minus b is equal to 0. And since this is really a norm, if the norm of a minus b is 0, that means that in fact a must be equal to b. If you go back to the old proof of this fact, the statement is exactly the same, and everything here is exactly the same, except that the absolute values got turned into norms. And then we added this one tiny little step at the end, which is saying that, well, if the norm is something and is 0, then in fact the thing has to be 0 itself. All right. So hopefully that's at least somewhat convincing that we can do many of the old theorems and many of the old calculations exactly the same way in Rd. And I'd suggest going back to earlier sections of the course, choosing a homework section, a problem or two, and just checking and convincing yourself that you can translate the proof without too much difficulty. All right.